Alright, so far with a lot of our rational functions, we've been able to find vertical asymptotes and holes. We've also been able to look at the domain, find the x-intercepts, which are the zeros, and the y-intercept is a skill that you've had since early algebra classes. Something kind of new we're going to start looking at is what we call the end behavior asymptotes. So, end behavior refers to what is happening at the ends of your graph. So, as x gets really big towards infinity, or as x gets really big towards negative infinity, what's going on out here on your function? Well, there's two different types of end behavior asymptotes that exist. The first is a horizontal asymptote. So, a horizontal asymptote would say that your function, as it goes to infinity, is going to run parallel to that line. Okay? It's going to get really, well, I shouldn't say parallel. It's going to run really close to it. It's never going to actually touch it. Now, something that's confusing about horizontal asymptotes is that even if you have a horizontal asymptote for end behavior, this graph might be able to be crossed over somewhere in the middle. Okay, so you are allowed to cross horizontal asymptotes. However, you will not cross a horizontal asymptote once you get out to really big numbers in either direction. So horizontal asymptotes, this would be the line, let's say y equals 5, or this one might be the line y equals 2. A very common horizontal asymptote that you're going to run close to is the line y equals 0. There are a lot of functions that run with a horizontal asymptote at 0. If you think about our reciprocal function, right? Going out this way, it's going to run really close to it, but it's never going to touch it. Going to negative infinity, it's going to get really close to 0, but it's never going to touch it. The other kind of end behavior asymptote that you might encounter is what we call a slant asymptote. So instead of running on a horizontal line as you get out to infinity, remember you can cross over the horizontals, you might have your function that, let's say your function looks like this, okay, as a piece of it, and this function might be running to infinity in the same way that this linear function is running to infinity. In which case we would write this as a slant asymptote of y equals, this is maybe the line x minus 4. Okay, so it's running to infinity in the same way that this function is. And then maybe the other part of this graph looks like this. And so in this direction, it's following that slant asymptote backwards towards negative infinity. So then the question is, how do I find the end behavior of my function? So you want to first simplify the function, just like you would when you are finding holes in vertical asymptotes. Okay, so factor the numerator, factor the denominator. And then 2, you want to look at the degree of the numerator versus the degree of the denominator. Okay? So, thinking about the degree of our numerator versus the degree of our denominator, after we've simplified our function, so we've crossed off any holes that have existed, okay, if the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is a horizontal asymptote. For example, let's say we have the function x minus 4 over x plus 2 and x plus 3, okay? We've already canceled out a hole that existed, or maybe there wasn't even a hole to cancel. So from here, we can figure out that the end behavior asymptote, okay, the degree of the numerator is 1. The degree of the denominator is going to be x to the second, because these are going to FOIL back together. Well, x to the second is bigger, right? Degree of the denominator is bigger than the degree of the numerator, in which case the line y equals 0 is our horizontal asymptote. Now, the next situation is what happens if the degree of the numerator is equal to that of the denominator. Well, we're still going to have a horizontal asymptote. This time, though, it's not going to be the line y equals 0. It's going to be the line y equals, and then it's based off of your leading coefficients. So let's say this factored, we'll again say x minus 4, and we'll say x plus 1 over x plus 2 and x plus 3. Well, if you were to multiply these back together, you would get 1x squared. Multiplying these together, you would get 1x squared. And the degree of my numerator is equal to that of my denominator, in which case the horizontal asymptote is going to be equal to the leading coefficients over one another. So this will be the line y equals 1. Okay, we'll do more practice, don't worry. The last situation is what happens if your numerator has a higher degree than your denominator, so it's greater than. So let's say this was x minus 4 and x plus 1 over x plus 2. Well, now these ones multiplied together are going to give me x squared. This one is just x to the first. Okay? This means that there is going to be a slant asymptote, and you have to do division to find it. Okay? So some people refer to this as bottom heavy, right? Denominator weighs more. Bottom heavy, y equals 0. Even heavy, y equals coefficients. Top heavy, slant asymptote, you gotta find your equation. Alright, so let's practice. Find the end behavior asymptote. Well, first step is always to simplify as much as possible. So this is going to be x plus 3, x minus 2, all over x times x squared plus 2. Nothing's going to cancel out, okay? But looking here, I'm going to have x squared on the top, and I'm going to have x to the third on the bottom. The numerator is less than the denominator, so the line y equals 0 is my horizontal asymptote. Okay? Horizontal asymptote, y equals 0. Next one, I can't do anything to simplify this, right? There's nothing that factors. So this has a power of x to the first and x to the first. Well, these two are weighing evenly. Negative 5x to the first over 2x to the first. In which case I'm going to have a horizontal asymptote at y equals the leading coefficient of the numerator divided by the leading coefficient of the denominator. Simplifying this one, the top's not going to factor at all. So 2x to the third plus 1 over, here I can take out an x, and this is going to be x plus 4, x minus 4. But nothing cancels out. So again, I want to think this is going to be x to the third power. And this is going to be 2x to the third power. These are even. So my horizontal asymptote is going to be at 2 over 1, which is just 2. Here, if I write this out 3 times over, nothing's going to cancel. Looking at the power of the bottom, it's much higher than the power of the top. So this is bottom heavy, and we're going to have a horizontal asymptote at y equals 0. Here, we're going to skip to this one first real quick. Here, if I factor all of this, okay, I get the same thing that's written right up here. And I found that this part gives me a horizontal asymptote at y equals 0. But I'm going to take that horizontal asymptote of y equals 0 and I'm going to move it up 3. So there is now a horizontal asymptote at y equals 3. Now, another way to do that would be go through and find a common denominator and add these things together and then do your analysis. But it also helps to just find the horizontal asymptote of this and then add to it. This one gets interesting. So, factoring wise, I don't believe this one factors. Should probably double check that before I say it for sure. No. And if we look at our weight of our numerator compared to the weight of our denominator, this one is top heavy. Okay? So we're going to need to find a slant asymptote. Well, our slant asymptote is going to be when we divide. So I put a 2 in the box because of our divisor. Minus 5, 5, 2, 4, negative 1, negative 2, 3. Our slant asymptote is just the function part, not including the remainder. So there's a slant asymptote at y equals 2x minus 1, which means that this graph, when you graph it, will follow the line 2x minus 1. Alright, this one again, looking here, nothing's going to simplify. The power in the numerator is greater than the power in the denominator, so there's going to be some sort of a slant. It's what we call top-heavy. In order to find that slant, I'm going to put -1 in the box. This is going to be 2, 0, and 0. 2, -2, 2, 2. Again, my slant asymptote is the function part of this, not including the remainder. So there's a slant asymptote at y equals 2x minus 2. Alright, moving along. This one does not factor. Right? You always want to try to simplify first. It'll make things easier for you. So looking at the powers, x to the second over x to the first, I know there's going to be some sort of a slant. -1 in the box. This will be 1, 0, 1, 1, -1, 1, 2. So my slant asymptote comes from this part, not including the remainder. There's a slant asymptote at y equals x minus 1. So again, what that means is that on your rational graph, you're following a slant line as opposed to running along a horizontal line. Okay? This one, x to the third and x squared minus 4. Well, I can factor the bottom, but this thing factoring doesn't cancel with anything up here. So we're still looking at a top-heavy function. So there's going to be a slant asymptote, and I need to do the division to get there. Well, in this case, I'm dividing by x squared. So this is where your long division skills are going to come in handy. X to the third plus 0x squared, 0x plus 0. I want you to try this long division on your own, so go ahead and pause your video. Okay, so looking at the division problem, just like with the other ones, we only care about the function that came out, not including the remainder. So there is a slant asymptote at the line y equals x. Alright, on any of these, once you've simplified, you can use division. Okay, don't be fooled by that. You can always use division, but the little shortcuts of bottom heavy, has a horizontal asymptote at y equals 0. Even heavy has a horizontal asymptote at y equals coefficient over coefficient, okay, leading coefficient. And top heavy needs a slant, which means division. These little tricks will kind of help you in being able to figure it out. But again, you should look at the top heavy, bottom heavy, and even heavy after you have simplified and removed any holes. Okay, so remove your holes first, then look at your simplified function.